Hey everyone, my name is James, and in this video we're going to be talking about the frequency domain response and second order dynamics. Let's get started. Before we talk about what the frequency domain response of a system is, let's just consider this spring mass system we have up in the top left hand corner. We have a mass connected to a spring with spring constant K. Whenever we're given a system like this, the first thing we should do is probably get the model. So we have a force being applied in our direction of motion. So that force F is the first force we'll consider, and we have a restoring force from the spring, which is given by Kx, where x is our position. And then we also have our inertial force, so we have mass times acceleration is equal to 0. And that's all the forces acting on this spring mass in the horizontal direction. We're going to ignore vertical. So we can rearrange this. So we have our mass times acceleration plus our spring constant K times position is equal to our force F. I'm going to call this equation 1. So this is our equation of motion for this spring mass system. And up until this point, when we've talked about how this system responds, and up until now we've only looked at exponential responses, we've been considering how it responds in the time domain. When I say the time domain, I mean if we plot time on our x-axis and our position x on the y-axis, we care how that position changes with time. So for instance, if I had, say, a radar dish and it was set to track a satellite and it had a big circular base that it could rotate on, a big poorly drawn circular base. X, in this case, might represent the angle of this dish as it goes around this 360 degree pattern here. So X could be equal to theta in this case. And so what we would expect is, over time, theta would trace out a sinusoidal pattern. And this is what we mean by the time domain response. How does this system change with time? So the time domain response is something you would directly observe and is probably going to be the most familiar thing to you. The frequency domain response, on the other hand, instead of talking about the position relative to time, we talk about a position or the magnitude of a position relative to frequency, where omega here is equal to 2 pi f. So it's a function of frequency. And this might be a bit unfamiliar to you if you've never thought about the frequency domain. But the idea is, rather than caring what's happening with the system at, say, 10 seconds, or what happens after, say, 1 minute, what we say is, okay, how does this system respond to an input, so in this case F, this force that we can apply, of a given frequency. So if F was a sinusoid that we were putting in here with a frequency, how does the position of this system change? And so if we were to put in, let's say at low frequencies, then there was no dampening and the position changed exactly with the force in. So by low frequencies, let's say less than 20 kilohertz. Now, omega would normally be in radians, but we're going to ignore that and just treat this like as a generic frequency. And let's say that this is a magnitude of 1, all the way up to there. And then afterwards, our magnitude drops suddenly. Well, what this left-hand side here is, usually what we'd actually plot is we are plotting a ratio of the output to the input. And we're plotting that versus frequency. So if the ratio of the output to the input is 1 and the input is 1, then you would expect the output to also be 1 in order for this to be satisfied. And so what this is saying is this is a system with a gain of 1, so whatever you put in is just passed directly through to the output. But beyond 20 kilohertz, if I put in an input of 1, I'm getting less out. This ratio is going down and down and down and down. And so this would be heavily attenuating the output. If I put in down here, if I put in a signal of say 1 volt, I might be getting out millivolts. And this axis over here would normally be in dB. On the left here, you'd have the magnitude in dB, and this frequency scale, it'd be in radians and would probably show it logarithmically, so you can see more information at once. But this is the idea, and this would be what we'd call a low-pass filter, because signals lower than 20 kilohertz all go through unchanged, but above, they're all heavily attenuated and you almost can't see them. A high-pass filter, conversely, would attenuate below 20 kilohertz and pass things beyond. And this doesn't have to be 1, this could amplify in that range or attenuate. That's totally fine, but these would be high and low pass filters. Now there's a bunch of reasons we care about the frequency domain. One of the main ones is if you're designing a system, it's much better to hand someone a system and say, I can tell you exactly how your system will respond to any input you give it that's within this frequency range. Rather than saying, okay, I'm going to have to poke the system at given frequencies and capture a whole bunch of time domain plots in order to figure out how it will respond. And so this becomes a really useful tool. And what you'll find is going forward, you'll probably work in the frequency domain much more than you will in the time domain. A signal that looks horribly messy in the time domain can usually be very simple in the frequency domain. For example, if this was rotating at a constant rate and was just a sine wave with a frequency of 2 hertz, in the frequency domain at 2 hertz, you would just have a peak. And this would be it. This signal only has a free component at 2 hertz if it's a pure sine wave. This signal has no component out here, and it's just here. So we know that this is a sine wave at 2 hertz. A square wave would have harmonics, so we'd get extra peaks. So you can actually tell a lot about the time domain shape of a signal by looking at its frequency domain. Okay, so we know what the time domain response is. We have an idea of what the frequency domain response is, and hopefully by the end of the video, you'll be able to see how useful it is. How do we swap between them? Because there is a transform, there's several transforms that let you swap between these two things. So if you have one set of data, you can recover the other. In this case, we're going to be using the Laplace transform. Now, the point of this video isn't to teach you where the Laplace transform comes from or how it's developed and things like that. I'm just going to give you enough information to be able to use it in order to obtain this transform. The only thing you need to know about the Laplace transform in the context of what we're doing here is that differentiation in the time domain is equivalent to multiplication by s in the Laplace domain, where if t is our variable of time, s is our variable in the Laplace domain. And in the frequency domain here, we have omega. So let me just write down what this would look like for a differential equation, a generic one. So let's say we have x triple dot plus x double dot plus x dot plus x is equal to u dot plus u. The Laplace transform of this differential equation would look like s cubed times big X of s. So these little x's are in the time domain, and the conversion is into the Laplace domain of s, plus s squared with big X of s, plus s x of s, and I'm hoping you can see the pattern emerging here. S u of s plus u of s. And so the pattern here is each derivative corresponds to a multiplication by s. And where we don't have a derivative, we just straight up get the Laplace variable. There's a lot more to the Laplace transform, but this is all we really need in the context of this video. Now there's two things I need to clarify here. The first is this transform would normally have extra terms. We would normally have to consider the initial conditions of the equation. So if you look up this transform when you're researching the Laplace transform, and I encourage you to, you might see initial conditions. The reason we've ignored them here and that we can going forward is because we care about what's called the transfer function of this system. So this ratio of the output to the input, this x over u, we call that g of s. And this corresponds to what's called the open loop transfer function. So when we've been talking about open and closed loop systems, this would be the transfer function that corresponds to the open loop system we have here. And it tells us how the output of the system changes for a given input. So when we consider a transfer function, we can assume that we have zero initial conditions, and that is a property of the transfer function. So in general, this Laplace transform actually has initial conditions. So keep that in mind. The only reason you can do this approach and simplification is because we are dealing with transfer functions. So now that we've got that, let's apply it and see it in practice to our equation 1, which is the system we care about. So we have our mass times s squared, big X of s, so x in the Laplace domain rather than the time domain, plus k of big X of s is equal to big F of s, where this f was in the time domain, because this whole equation is. We have an equivalent of equation 1 in the Laplace domain. So we can rearrange it a little bit more. And so we have x of s times m s squared plus k is equal to f of s. And if we swap terms around, what we find is we have an equation of the form our output, so the position of the system, over the input, the force we're applying, is equal to some transfer function. So this is our open loop transfer function. Still in the Laplace domain. If we want to consider this system in the frequency domain to get our plot over here, one way we can do this is, in this case, we let s equal to j omega, where omega is our same omega as here, and we substitute that back in to what we'll now call equation 2. And we see that our g of s, so x of s over f of s, is equal to 1 on m s squared would be omega squared, and j squared would be minus 1, plus k is equal to 1 on k minus m omega squared. And this, oh, actually, this should be j omega because we've made the substitution. This function describes how our system changes, so this ratio of the output to the input, as a function of omega. So now we have a model for the frequency domain response of our system. And so what we could do is, since g of j omega here is technically equal to x of j omega over our f of j omega, if we picked an exact input we want, well, we can just multiply this side by that input and see exactly how the position will change for any given input, f of s. And this is why this is useful. So in this is kind of a general, in a block diagram form, this is quite general. And so we would have our f of s as the input, our transfer function here, k plus ms squared. We can pick whatever input we want, multiply it by our open loop transfer function, and see exactly how this will change. Okay, so we know how we have a model for our system in the time domain. We have the frequency domain equivalent, and we can produce a plot of this open loop transfer function in order to get the frequency response of our system. Let's do that now in MATLAB. So I've just swapped over to MATLAB, and I've written up a tiny bit of code to generate a transfer function, that's what this TF command is, of the system that we just drew. And I've made some assumptions. I've just said let the mass equal 1 and the spring constant equal 1. We'll get to this R value in a second. And what I've done is this pzmap command, so it produces a plot of the eigenvalues of the system in this case. And what we see is we have two complex poles or a complex conjugate pair with 0 real component and an imaginary component of 1. And we can see this pretty easily if we go back to our transfer function. Generally, when we're considering the poles or the eigenvalues of the system, we would just use the Laplace domain equation. And in this case, the poles would be when this denominator is equal to 0. And a bit of a hand-wavy reason we call that a pole is because if you were to think about a plot where this denominator went to 0, well, this transfer function would shoot to infinity because it'd be 1 divided by a number approaching an infinite one. So the frequency response would spike up here. So we call that a pole. And conversely, the zeros of the system are when this numerator is equal to 0 because, well, the output of the system will be 0 at that point. That's a bit of a hand-wavy response. There are real subtleties to the poles and the zeros, especially when we start talking about systems that aren't single input, single output. But for now, you can think about it like this. So we care when this denominator is equal to 0. So ms squared plus k is equal to 0. And that is going to be true when s is equal to plus or minus j, the square root of k on m. And we've just pulled the k across, divided by m, taken the square root of the right-hand side, and the minus created the j, and we're left with this. So what you can see is if our k over m is equal to 1, like it is in our MATLAB example, we should have s is equal to plus or minus j, or plus or minus 1 on the imaginary axis. And that's what we see. We see we have a complex conjugate pair with that exact thing. So the MATLAB example matches our theory, and we can get our poles this way. So we'll swap back to MATLAB really quick. So now we're back in MATLAB, and we want to see what the frequency domain response is. In this case, I'm going to produce what we call a Bode plot of this system. And you can see here, it's now produced what we call a Bode diagram. Please ignore the phase component. We'll get to that later when we're dealing with complex systems. For now, we'll treat this magnitude 1. So here we have the magnitude of our transfer function in dB, like we were talking about, and the x-axis here is our frequency in radians per second because we're dealing with omega. And what you see is the response pretty much sits at, this will be about, this would be roughly like our 1 where we started off, because remember this is in dB, so 0 dB is equivalent to our 1. And we come across here and we see it's relatively flat, and then at this frequency here, we get this massive spike in the gain, and then we start to see that roll-off we described. So this is kind of like that low-pass filter, except we have this huge spike. Where does that spike come from? Why is that happening? And we did not see that with our first-order systems. So let's cut back across, and let's see if we can't figure out what this spike is. Okay, in order to see what that spike is, let's consider our frequency domain equivalent of the transfer function that we had here. So I just want to rearrange it a little bit, and I think that's going to help illustrate what that spike is. So let's just pull the k out from the denominator so that we have 1 minus m on k omega squared. And if we collect everything in this square term, what we can actually get is 1 on k, 1 minus omega over omega n squared, where omega n is equal to the square root of k on m. And you can see if we take the square root of this here and we square it and then we pull it underneath, it's obviously going to flip these two, and that's where this comes from. Now, why did I just do this? There's a very good reason I did this, and this omega n was not some random choice of variable. Omega n is what we call the natural frequency of this system. So if we were to plot out what's happening again over here, what would this transfer function do as omega approaches omega n? So omega n is some fixed value, right? The spring constant is fixed and the mass is fixed. So the natural frequency of the system we're talking about is some constant thing that is determined by how the system is built. So there's some frequency, omega n, corresponding to this ratio that we're considering. So what happens as omega approaches that? Well, if omega, so our frequency, if we put in a signal at that frequency, if our omega is equal to omega n, then this term is just 1, and 1 minus 1 is 0. So we have 1 on 0, which is our infinite term, and that's our big spike. If omega is equal to 0, well, we have 1 divided by 1, or 1 over k, and that's where we start off here. So we get some scaled version of that 1 on 1. And in our other example, well, k was equal to 1, so that's why we started off at 1. And then as omega goes off to infinity, this term becomes much bigger than this one and dominates, and we get 1 over some very large number, and we kind of shoot off. And that's actually exactly what we had in MATLAB. So this is our MATLAB plot, and that peak was corresponding to what we call the natural frequency of this system. And this peak is what we call a resonant mode of the system. So this is when the system resonates. And so what that means is all the frequencies below this point, everything's fine. The gain's roughly sitting at 1, but as soon as we put in something of this frequency, the gain will shoot right up. So if this was something where we needed the speed controlled at a constant speed, if our frequency of whatever signal we're inputting into the system shifts along and it hits this point, well, the whole system output, we're going to suddenly have this massive spike in our speed. So if this was like cruise control of a car, we're suddenly going to lurch forward and probably ram into the person in front of us. So we want to avoid these peaks. If we were to use this system here, we would need to either ensure that our signal F, or our input force, had a frequency less than this point or greater than this point, depending on what we wanted our output to be in terms of attenuation and things. Now, there's two ways we could move this frequency. Say we actually needed to run this, say this corresponded to 10 hertz and our system needed to rotate at 10 hertz. We couldn't afford to have it run at a lower or higher frequency. Well, our only option would be to move this value. And there's only two ways we can achieve that. The first one is to change either the spring constant or the mass, because they're the only things that can change this value. But generally with a physical thing, you can't just arbitrarily change it. There are certainly instances where you can. So in stabilizing adaptive mirrors and things, what they tend to do is those mirrors have a frequency response that kind of looks like this, and they have low frequency resonant modes like this. And what they do is, if your mirror, this is going to be a terrible picture, but if your mirror is sort of sitting there on a mount, you can make a different mount, which will change the dampening and move this thing and might help. But if you can't physically change your system, and you can't physically change the spring constant or the mass, you need that. Our only option is to design a controller or a replacement for this F signal that controls the system the way we want and also changes this equation in the closed loop such that this peak is moved. So now let's consider, I guess, the mechanical version of that. So changing the mirror mount. What might we do? Well, we might add dampening. And that's generally what changing the mount would do. So in this case, if we can't change the spring constant and we can't change the mass, let's add a dampener in. And it has a dampening constant of R. So our equation of motion will change. Everything else will stay the same. We're also going to have the dampener trying to dampen this motion as we pull away. So we're also going to have an Rx dot term that we didn't have before. So we can rewrite out our equation of motion once more. So we've got plus Rx dot plus Kx is equal to F. And so that's our equation 1. And so we have our time domain equation of motion like we got last time. And we can once again swap it across to the frequency domain. So we'll take our Laplace approach that we did before. So we have m second derivative, so s squared big X of s in the Laplace domain, plus r s first derivative of big X, plus k no derivative of big X is equal to f of s. And we'll gather up terms again. So we've got m s squared plus r s plus k of x of s is equal to f of s. And our transfer function, x of s over f of s is equal to g of s is equal to 1 on ms squared plus rs plus k. And just like last time, let's check the poles of this system and check for stability. We'll just use our quadratic formula to solve for this. So we'll have minus r plus or minus the square root of r squared minus 4mk over 2m. So we'll have minus r plus or minus. Let's, in this case, actually, before we go on, let's substitute in the values we picked in MATLAB. So remember we said m was 1, k was 1, and we had this value of r that we didn't use. Surprise, surprise, this is what it's used for. And we'll let that equal 1 as well. So we get minus 1 plus or minus the square root of 1 minus 4 over 2. And we should have minus 1/2 plus or minus, what is that? J, the square root of 3 on 2. This is where we would expect the poles of our open loop transfer function to be. We would expect the real component to be at minus 1/2, and we would expect it to be a complex conjugate pair. This real component is significant. In our last example, before we had the dampening, our poles, remember, or the eigenvalues, had 0 real component and were on the complex, on the imaginary axis. This is what we would describe as a system as marginally stable. If these were slightly over into the right half of the complex plane, the system would be unstable. And you could see this if you solved the time domain equation for this system here, you would see that there would be terms that would grow unbounded. And here, you would expect to see a time domain response that oscillated, and it oscillated forever. It didn't explode out and it didn't shrink down, it just went on forever. And that's why we call it marginally stable. A stable system, like we have in this case, would have at minus 1/2, we would have our poles in the complex plane here. It's still going to oscillate. This complex conjugate pair ensures we get this oscillatory behavior, but the real component means it's going to die down over time. And so eventually, this system will die down to a constant steady state value, or it will die down to 0. And so this is good. This is stable. The last one was what we would call marginally stable. And it's important to carry on that distinction between marginally stable and actually stable. Because, I mean, when we say it's marginally stable, we say it's marginally stable when the real component is equal to 0. But how many things in the real world have you ever seen that are actually true 0? It might be 0.0001 or something like that, or even like the slightest knock could transfer this function if there's noise or things like that. So a marginally stable system is not generally something you want to allow if you can actually make it stable. Sometimes there are definitely reasons for it, but keep in mind marginally stable is not the same as stable. That system is going to oscillate forever, and you're going to have to hope that nothing knocks the eigenvalues into the right half of the complex plane. Okay, so let's jump over to MATLAB again and see what the response of this system looks like. So I'm back over in MATLAB, and what we can do is, you'll notice the only difference between our original transfer function and this new one is this R of S term. So I'm just going to add that in MATLAB. And if I rerun this script, what we see is our poles and zeros are exactly where we expected them to be. So on the real axis, they're at minus 0.5, and we have this complex conjugate pair on the imaginary axis. And now our response of the system looks very different to how it did before. We no longer have that massively sharp peak. This one's a bit hard to tell actually because it's quite flat here. So let's take that dampening value of 1 and lower it to say 0.2. So this is our value of R. And we'll run this again. And what you've seen is, hey, the peak's come back. And it's actually quite a bit taller than it was. And if we look up here at the poles again, we see, okay, by changing R to 0.2, so you remember the real component was just minus R over 2, so we're at minus 0.1. We've moved closer on the real axis towards 0, and the imaginary component has changed, but it's still imaginary and oscillating. The closer our real axis component gets towards 0, the taller this peak here gets. And so the dampening term gives us power to control the shape of this peak in this case. And so no dampening, we get that sharp peak that we had before, and with tons of dampening, the system barely moves, but we get no peak. Okay, so I've just updated the script here so we can see what happens with a very small amount of dampening, so say 0.1, and a large amount where our R term is 1. And with a small amount of dampening, we get the peak we expected, but it's been reduced. And when we have that maximum amount of dampening again, we can see that the peak has almost completely disappeared. And instantly, this kind of looks like a better response. Why wouldn't we want this? Hey, we've completely gotten rid of that resonant peak. We've got this nice flat area and a roll off. Sometimes you may want that. But generally, the trade-off here is if we come and look at, say that we have this minus 20 dB point, and we trace it across, and we look at where we are on the plot. And we're here at, what is that, omega is equal to, let's call it 3.5. If we scroll down to our plot where we have the dampening value of 1, and we go to the 20 dB, and we come across, we'll actually find now we're at closer to 2.5, 3. And this 20 dB point has moved right in. This is a bit of an extreme example, but in general, you might need that little bit of extra bandwidth in this case, and so you might not be able to actually pull in the response like this, so it'll limit the amount of dampening you can apply. By changing that dampening, not only have you lowered the peak, but you've also changed both sides of the response, and you just need to consider exactly what it is you're looking for in your overall control objective to say whether or not that's okay. And so that's the introduction to second order systems. In particular, the things that are important here is if we have a complex component to the eigenvalues or the poles of that system, we're going to get oscillatory behavior. If those poles have no real component, our system will be marginally stable. If they have a positive real component, it will be unstable. If they all have a negative real component, it will be stable. If we were to get rid of the oscillatory behavior, so the imaginary component, you'd see we'd actually get our poles on the real axis and we'd be back to just summing first order responses. So also, we've spoken about the frequency response, and we've said up until this point, we've looked at the system in the time domain. So how x, our position, changes with time. And now we've shifted our thinking to think about how x changes with frequency, because this is going to be a much more useful tool for both analysis and design, and this is going to come up a lot. As always, if you have any questions, please feel free to reach out, and thanks for watching.